Hello, people who are watching the recording. The actual event will start in about 5 minutes, okay?
This seems to happen a little too often to me. I'm just going to point that out.
Okay.
Yes.
After I start presenting, hit on there, change that, and now what's been streamed is just that. People will be able to see the slides from the recording and in the live stream.
Ah, okay.
And then to pan back out, click on that button.
So when you so we start when we hit record.
Yeah, well, it's already recorded.
Oh, it's already recorded.
It's already
Yeah.
live streamed. No one knows the live stream yet. Yeah, you can do that, and now people.
So can you leave it at that level? Or because you want to be able to see yourself to start with, yeah.
Yeah.
Or you could stand in front of it. I'm happy to do whichever you like. What you tell me what you like.
I reckon so recording, and this will be on the recording. So yeah.
So start with that, and then I just click on it, and it'll zoom in to what we want.
Use two fingers to stretch it to the right side.
Okay. Done.
Yeah, and I think it's still fun because otherwise everyone will get sick.
Pretty much, yes.
Okay, brilliant.
What style? Because I've got there's the two styles. There's the one that is a long skinny, and then there's a long one that's a bigger rounder.
We'll have a look at it because they gave me a pack of each, as well as all the show. So maybe I can say it.
That is, and they even split in your me such thing. It's all beautiful. It's been interesting to watch.
Yeah, good. I'm off to San Fran weekend. I'm going to do a lot of product
Surprise. Because we have IP that.
So basically, yeah, working makes sense. Yeah, but yeah, really good. Still on the cards? Yeah. Anytime. I've got to be something early in the week. I'll call them yeah, as I say, a lot of the stuff we've got, but it's not very well. So I think, I've seen as we do that stuff. So it's that.
Or they kind of going, it's nice to know that we don't really need it to want to know it. To be able to do what things need to do.
Yeah, because I said, like, interestingly, a lot of the reason why I think it's just so that
No, I agree. Cool.
Yeah, I'm going to take it on the plane and just freshen up because it is pretty good.
So is this the second half? So when you first gave this it was a combined. Is this the second half of that one?
Yeah,
it's a mix.
It's a mix, and it also includes BLS signatures, which isn't something that I get originally, but something that I was asked for. So that's where you can combine turns out the sharding effort they wanted to
Yeah.
so
Startup life. That's good. It's tough for me because I can develop, so I can do I can make stuff in that.
There was none.
So I see you get
So I found that the cycle through your first one.
Yeah.
Anyway,
I think the one that
we've got someone on the live stream. Cool. Yeah, done. Next to the last week we had a people, so just there you can see a number, which is 1.
Well, she was a bit ill today.
Oh yeah,
She was,
okay, let's grab the clicker.
that's probably a good idea.
Yeah. Okay, hello and welcome everyone. So today we're going to talk about cryptography. So back about a month or two ago we did a very basic introduction to security, and so now I'm going to talk a little bit more about actual cryptographic algorithms. Okay, so let's take it away. And Brett is working out the zooming into the slides business. Cool, we are live. All right, yep, so that's the agenda. So in August, I'm going to do part 3 of this whole presentation, and we'll keep on going. So I'm going to walk through a whole lot of different types of algorithms, and so let's start off at message digest, the most basic type. So a message digest are also known as hash functions, but cryptographic hash functions. So you can't think of them as like, say you've got a map and you're doing a hash there, as you might do in Java or something like that. This is cryptographically strong, so a much higher level of security. So the idea is you have a variable length input and you get a fixed length output. And when you're thinking about cryptographic hash functions, you should be really thinking about their security properties. And so the first one you've got is this one here called pre-image resistance. And so the idea of pre-image resistance is, given the output, hx, you can't work out what the input value is. And second pre-image resistance is, given an output value and an input value, you can't work out another input value that's different to that x value there that will hash to the same value. So that's second pre-image resistance. Collision resistance is, all right, so I've got, I can choose any 2 values and they will hash to the same number. So when you're thinking of those 3 security properties, you've got to think about their security strength. And so when if you've got classical cryptanalysis, then say n is the number of bits of the hash. So say if you've got a, say, SHA-256, it's got 256 bits in the hash function. And so the security strength of it for a pre-image resistance property is 256. And ditto for the second pre-image resistance. But because of birthday attack style issues, it's n on 2. So essentially it'd be 128 bits security strength when you're thinking from a classical cryptanalysis approach. If you assumed you had sufficiently capable quantum computers, though, you can do essentially a search and using Grover's algorithm, and then that'll bring it down half the security strength for pre-image resistance and second pre-image resistance. A person whose surname starts with A, but I can't remember off the top of my head, they've proven that the lower bound of assuming someone can come up with the correct algorithm will be n on 3. Assuming, so there's someone comes up with the right algorithm and we've got quantum computers that are sufficiently powerful. So when we're talking about sufficiently powerful computers to do this sort of thing, we're talking 2040, 2050 maybe. I mean, it could be 2025, who knows, but it's, in all likelihood though, it's 10, 20, 30 years off. So we've got some algorithms here. These are old ones that you should not use. So you've got MD5, that's a message digest function which has been used all over the place historically, but you shouldn't be using it now. Preimage and collisions have been found, so someone has been able to find a preimage that will match so an X value for a HX value. Right into 160, it's only got 80 bits of security strength, so someone could brute force that. SHA-1, a collision has been found. So for SHA-1, there was someone had a PDF file that had SHA-1 in red, and then another one which had SHA-1 in green, and they had fiddled around with a couple of hundred bits, and they had it so that it hashed to the same value. So that's a collision. That came out about a year ago. And so you shouldn't be using SHA-1 because its collision resistance property is broken. But saying that, its pre-image resistance property currently is okay. No one's found a hack for that. So hence you should still be okay for Ripen 160 and SHA-1 if you were using those properties. But the thing you've got to think about is you'd have to justify it to whoever's doing a security audit that you're really not using collision resistance when so you're thinking you aren't, but maybe you are. So you have to justify that you're not using the collision resistance security strength property. So another thing to think about when you're looking at digest algorithms is this diagram here, which I've stolen from this person's paper down the bottom here. So what they showed was, so this is essentially Moore's law increase in computing power and the ability to break algorithms, in particular hashing algorithms. And you've got a range of hashing algorithms that, someone's found a weakness, and that weakness, it hasn't completely broken the algorithm, it's not down to 0 bits of security strength, but it's gone from 65 or so down to 20, or from 80, and sometimes the break, because the algorithms are very similar, affects all of the algorithms, where sometimes it only affects some. So what this is really showing is that no one algorithm is good. You've got to assume that at some point an algorithm will break, which is always good to keep in mind. And this is why in the previous presentation I was saying, look, you really want to have crypto agility, the ability to change cryptographic algorithms. And that's because things break. Okay, so NIST is a part of the Department of Commerce over in the USA. And so they've said that really, as of 2011, we shouldn't be using 80-bit security strength. And so that means if you've got a 160-bit digest function, you really shouldn't be using it. So I should have hidden this little bit here and said, hands up, who knows where we use a 160-bit digest function. So, as we all know, it's in the address hash. So if you can work out a way, which I've written a paper on, how you can, in Ethereum, use this 160-bit address hash and generate a collision, set it up so that you can have a colliding address. And so hence, in Ethereum and Ripple and Bitcoin, you've got a problem here because the address hash or the hash function being used is too small. So this table here looks at various algorithms from the SHA-2 family. So NIST ran a message digest algorithm competition years back and said, look, we need something to replace SHA-1. They came up with this list of SHA-2 algorithms. And so, as you can see, you've got the bits of the digest size, which reflects back to their pre-image resistance, and half of it is your classical cryptanalysis collision resistance. When SHA-1 was being broken, they said, ooh, what we really should do is SHA-512 is stronger than, is better than these other algorithms because it's got better internal state, it's got bigger internal state, which makes it harder to break. So they created a SHA-256-512 and SHA-384-512, which are essentially you do SHA-512 and then truncate the digest function. So you've still got the security, the internal security of SHA-512, but then you truncate it down so you've only got the size, the 256-bit security strength. But if you're an attacker, you'll be able to break this one before that one. Okay, so the SHA-2 family though suffers from length extension attacks, and so that's essentially where you can have, if you've got the hash of a message and you've got the length of the message, then you can essentially append another message on and do a collision. So the people in Bitcoin, how they overcame that was to have wrap the SHA-256 in the ripened 160. And I think as well they were thinking, well, if we have different algorithms, then if one's broken, then the other's good. So that's how they got to that. Yeah, so then the SHA-3 family came along. And so the SHA-3 family, there was a competition to work out this digest function. And so this is the one that was attacked. And the thing is that in Ethereum land, they went off and used this algorithm, but they used it before it was standardized, and hence the formatting is slightly different from SHA-3. So this gets around the length extension attacks. You don't have to worry about that. You don't have to have a nested hash function approach. And so again, its digest size and it matches for its pre-image resistance and is half for its collision resistance. Okay, so sometimes people use truncated digests. So the thing to think about with truncated digests is if you truncate, say, a 512-bit digest down to, say, 1 bit, say, as the extreme case, then there are only going to be 2 choices, aren't there? So your security strength is 1. And if you truncate it down to 2 bits, there are only going to be 4 choices. So again, you're only going to have 2 bits. So if you truncate it down to 160 bits, you've only got 2 to the 160 possible combinations. So as you truncate a digest, you're essentially limiting its security strength. That's something to keep in mind. Shake is a modification or another usage of SHA-3. So SHA-3 is what's called a sponge and squeeze algorithm. So it absorbs essentially the bits in. So you know how we had you feed in as many bits as you like. So you feed them in and then it squeezes them out. And so normally you squeeze out just that digest size, but shake is a usage of the algorithm where you keep on squeezing and squeezing and squeezing and generating more and more bits. So it's like a bit stream generator based on that input. So as a recommendation for these algorithms, so Ethereum's use Kirchhoff 512 and 256, and generally you're going to want to use those, simply because you've definitely got those available to you. But you might choose to use SHA-3 256 as well. That could be good, but it could also get confusing because in Ethereum, in places, Kirchhoff has been denoted as SHA-3. Don't forget about crypto agility. If these algorithms suddenly become broken, you need to have the ability to switch algorithms. So you should be keeping that in mind. Okay, everyone's still following and all good. So let's talk about symmetric key crypto, also known as secret key cryptography. So you use the same key to encrypt and decrypt. And yet you've got to distribute the key using some communication mechanisms that's out of band. And so the idea is you've got plain text, you've got a key, the same key at the other end, you encrypt it using that key, using the algorithm, you get ciphertext, you decrypt it using that key, you've got plain text. So, you've heard of, there are block ciphers and there are stream ciphers. Block ciphers, they take data 1 block at a time. So it might be 8 bytes or 16 bytes. And then you've got stream ciphers, they essentially process 1 bit or 1 byte at a time. And so you've heard of DES, I'm sure. Who's heard of DES? Everyone's heard of DES. Fantastic. Okay, so DES is a block cipher, as is AES. RC4 or CHA-20, they're stream ciphers. So the block cipher modes, they essentially change the way that the block ciphers work. And so some of them will allow you to take a block cipher and turn it into a string cipher. Some require padding. Some add authentication. So encryption is not the same as authentication, as we'll remember from the last talk. So you can add authentication so it's all done in one process. And some require initialization vectors. Yep. So, DES developed in 1974, became a standard in 1977, but it was withdrawn in 2005. without reading, why was it withdrawn? Stony silence. Okay, it was withdrawn because 56 bits isn't very big. 56 bits is something that you could easily brute force these days, so you wouldn't use it. Triple DES came in 1978. It had a longer key size. It essentially used 3 sets of DES. And so you do DES to encrypt, decrypt, and encrypt. Now, you could use it, say to do encrypt, 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 or decrypt, 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 but if you essentially do anything but EDE or DED, then it is not secure, which is a bit of a problem. And the other thing that they found was that there's a related key attack that you can do. So even though you've got this big key, it's not as the security is only about 2/3 of the key size. So essentially, when you had a 112-bit key, you were only getting yeah, 80 bits. Yep. Yeah, when you had a 112-bit key, you're only getting 80 bits, and when you had a 168-bit key, you're only getting 112 bits. So it's slower than AES, which has come out since Triple DES came out, and it's just not that secure. So 112 bits means that by 2030, you don't want to be using this algorithm anymore. So AES came out, and Jan Damon and Vincent Ryman developed it in 1998. Originally it was called Rydal, and so it became a standard in 2001. It uses a range of key sizes. So AES 128 there's been a slight break of it, but only down to 126.2 bits. And 2 to the 126 is still a really big number, so that's still pretty secure. One thing to keep in mind, AES has become so universally used that it's now in CPUs, and so any CPU that's got the AES-NI instruction will be accelerated, it'll be fast. So when we're talking about modes, you've got a whole stack of modes. This is only a small subset of possible modes of operation. So let's quickly walk them through. ECB, electronic code book, that's essentially you're just using the basic cipher, and so whatever goes in comes out. So there's no inter-block encoding. CBC, you're chaining the blocks together, and but there have been attacks on that, and so you shouldn't use that. CFB, the initialization vector's got to be random. Not many people use that, or OFB. CTA, you'll see that used quite a lot. That can be done in parallel, but you've got to, and it can allow random access, which is really good. But you've got to be, it becomes completely insecure if you reuse the counter value. CCM and GCM rely on CTR, they're authenticated encryption schemes. So they're really good because then you can't muck up the way you're doing authentication and encryption together, because it's all done in one packet. But whatever you do, do not repeat the counter value, otherwise they're not secure. So, really good algorithm, but there's this thing to watch out for. So Cha-Cha 20 with Poly 1305 is another algorithm that you'll hear kicked around. So Cha-Cha 20 is a stream cipher developed by Bernstein, and Poly 1305 is an authenticator. You can use the two together, and it's a bit like doing AES GCM, so you're getting authenticated encryption. So is it going to be better for you or worse? Well, on general purpose CPUs, it is faster. However, if you've got the AES-NI instruction on your CPU and you're able to take advantage of it, the AES will be faster. So, it depends on the situation. One-time pads. Okay, so if you're into secret squirrel land and you've got these teensy-weensy pads, look at how simple that is. Or maybe if you've got kids and they want to have secret messages, you can have this idea of you have a key string and you XOR. So XOR is where you combine the bits together. Who doesn't know what XOR is? Fantastic, we've got the right audience today. Okay, so you XOR in the key with the plain text, and then you do the reverse to get the plain text back from the ciphertext. So what you could do is you could say, all right, let's everyone get that Harry Potter book, and then the start of the key string could be 33, which is page 33, line 5. And then what you do is you use the characters in that book, then you've both got exactly the same book as your key string. And then you can use that to create some perfect ciphertext. So it's not authenticated, so someone could put something in the middle, potentially, and make it, destroy your ciphertext. Also, the keys is going to be exactly the same length as the plain text. So again, that could be, lead to people knowing how long the plain text is, which is an attack in itself. So my recommendation is use AES-GCN with a 256-bit key. And the reason is that it's authenticated encryption, so you can't muck up your authentication. And 256-bit will be good even when quantum computers come along. And also you get FIPS as well, which is good. Okay, message authentication codes. They're also known as MACs. So with a MAC, the idea is you're putting plain text in, variable length, and then you've got a key there, and then you're getting a fixed length output. And so the idea is that anyone who's got that key can verify that it was you who sent that message authentication code. So plain text in, key there, same key over there, same algorithm. You send the plain text and the MAC, process it, and then you compare the two MACs at the end. And if they're the same, then you're all good. So if Brett sends me some plain text and we've got the same key that we've shared out of band, then I know it's Brett who sent me that text because he's the only one with that key. Okay, so a lot of the algorithms are HMAC and then followed by a hash function. There's also one called GMAC. Also, you can use Kitchak, and so you can use that as well. And there's an algorithm called KMAC. Okay, HMAC GR256 is really widely deployed, and hence is probably a good choice. Assuming there are no algorithmic breaks, though, it should be good in the long term. Okay, so I've sped through that. Any questions? We're all good. Okay, asymmetric crypto, also known as public key cryptography. So you've got two keys, one's a public key, one's a private key. Private key you keep to yourself, public key you give to everyone. And so you can use it for encrypting, say with your private key, and decrypting, or encrypting with the public key, decrypting with private, or signing with private, verifying with public. So, if you are doing design documents or architectural documents or specifying a system, for the cryptographers who might then be asked to review it, it will really help them if when you're specifying a public key, you use a capital letter. And when you're talking about a private key, you use a lowercase letter. So this is just for design documents, because otherwise it gets very confusing, because if you're just used to seeing public keys in capital letters and private keys in lowercase letters, it gets really, really confusing. Okay, RSA. RSA is an algorithm developed by Riva, Shamir, and Edelman back in 1977. Apparently, I think it was they were having drinks over some Jewish festival, so it came up with some great algorithm. So it sounds like, key to having a great algorithm is having a great party, obviously. Okay, so the idea is that you have n equals p times q, so n is the modulus. And so the idea is that, say, you think, all right, so 3 times 7 is 21. Well, if I've got 21, what numbers factor into that? So you can think, oh, yeah, 3, 7. So that's nice and easy. If it's a really big number, much harder. So the public key is the modulus and the public exponent. The public exponent these days is always chosen as that number there, 2 to the 16 plus 1. People in the past have used 3 and 17. The thing with that is that you can maybe work out the cube root of something or the 17th root and try and do some sort of brute forcing or some sort of attack, whilst doing the 65,537th root of something and trying to do something is much harder. So generally that's a good number. It's a prime number. and then you can calculate D by that equation just there. So, and D is your private key. So if you're doing encryption, what you do is you've got your message to the public exponent, the modulus is the ciphertext, and then you're doing the same mathematics, but in reverse with the private exponent, getting your message back. So obviously you need to use a bit of padding, otherwise it's just not, it's just maths. Someone would just multiply it by some number and then change everything. So you've got to do some padding so you can detect that someone's just multiplied the numbers. You hear about 2048-bit RSA. ECC, so a guy called Koblitz and Miller, I don't think they worked together, but they independently came up with it, I think, in '85. And so this is an elliptic curve, but they don't actually look like this because they're essentially digitized. And so the idea is that the maths involved is harder, so you can get away with smaller keys. I think that's the guts of it. And so there are lots of different types of curves. And defining a curve, you have all these numbers. And in fact, someone who was, being inspired when they were defining this curve in this NIST standard has decimal there and hexadecimal there, which is particularly perverse, I think. So anyway, rather than individual application developers typing in all of that, people have named curves. So you can just say, I want to use P256. Okay, quiz question for everyone. What is the curve used in Ethereum? Oh, yep.
I don't know, the full name 256K something?
Yes, K1 I believe. Yeah. Top of the class. Yeah. And so that's the thing. Having a named curve makes your life so much easier, because then rather than everyone hoping to get all those numbers right, you can just specify in your code some nice short number or identifier, and then the parameters can be loaded up by the cryptographic library. So for ECC, you've got a base point, and from that generated point, you can generate all the other points on the curve. And so the order is the number of points you could possibly have on the curve, and the EC private key is just a number, so it's a scalar between 1 and the order -1. And the public key is a point on the curve, so it's the private key, so that number times the base point. And so the idea is that the order of the curve is going to be something like 2 to the 127 or something of that size, so it's still a really big number. So the good thing about ECC, at least for classical cryptanalysis, is that the key sizes are much smaller, and certainly by the time you're getting at 128-bit security strength, your ECC is actually faster than your RSA. So you're not only is it smaller key size, but it's actually faster to execute. So you shouldn't be using, say, 1024-bit RSA or 160-bit ECC anymore, and you really don't want to be using, say, 2048-bit RSA post 2030, or have anything that could be recorded and then later decrypted back in 2030 available as well. So you've got to be thinking the information being protected shouldn't be relevant in 2030 if you're using RSA 2048. So what about, when we have these quantum computers, what happens then? So this is an interesting one. So when you've got quantum computers, the security strength of, say, sort of a 5-bit number, so if you were thinking about something like, say, 21 and 3 and 7, back in 2012, I think that was when that level of security strength was broken. So with a quantum computer. But the idea is that as quantum computing, the actual field settles down, we're likely to have a Moore's law increase in processing power, but we're not quite there yet. But when we do get there, then it'll be interesting to see, is it a straight line curve, or is it some curve, or how does this technology field progress? But the general feeling is sometime in the 2020s or 2030s, 26-bit security strength quantum computing will break, and so you'll lose the RSA 2048-bit keys. They'll be broken. But because of how ECC works, and because the discrete logarithm problem will be able to be broken, breaking a 256-bit key will actually be easier. So ECC 256-bit keys will be broken before RSA 2048 by possibly some years, but maybe it'll all happen on the same day as well. Depends on how the technology field advances. Digital signatures. Okay, so what we're doing is we're combining message digest and asymmetric cryptography. So I'm signing something with my private key, and any of you can verify it with my public key. So, how does it work? You've got some plain text, you message digest it, you've got a private key, you then sign it, and you have a signature. You send the plain text and the signature. You message on the receiving side, message digest the plain text, you get the digest, and then you put it into a verification function, and it's either going to be verified or not, as the case may be. So notice that you're getting authenticity, but that plain text is there, so you're not getting any secrecy. So if you look at the maths here, for RSA, it's very similar to what we were talking about before. For DSA, you've got you've got the message digest, and you're signing by the private key, verifying public key, so very, very similar. Key agreement. Okay, so the next piece of the puzzle. So, you know how we said we've got these symmetric keys and we needed to somehow or other communicate them out of band. So in the good old days, you'd have these guys and they'd have suitcases handcuffed to their wrists, and they would go from the central bank branch and they'd go out to some branch office, and then they would open it up and there would be the key. So that would be really annoying every time you wanted to go HTTPS something or other, to have some dude walk around with a handcuffed briefcase. So luckily for us, there's these guys who came up with key agreement. And so it allows you to agree a symmetric key or a secret over an insecure channel. And so there are two main algorithms. And so you've got Diffie, Hellman, and Merkle. And for those people who are looking at this going, what happened to Merkle? Diffie, Hellman, but what happened to Merkle? Poor Merkle, how does this work? So anyway, Diffie, went to RSA conference quite a few years ago now, and Diffie and Hellman agreed that really Merkle should have got some credit, but oh well. Anyway, it's too late now. But anyway, so the idea is that it all relies on something called the discrete logarithm problem. So it's easy to compute this, but it's hard to compute that. And so it's allowing you to agree these secrets over an insecure channel. So what you do is, you've got coolstock.com. So you remember from last talk, we had some website, we had Alice who was interacting over the internet. So she generates B, and coolstock generates A. And so you've got G to the A mod P, and so G's the generator, P's the prime, and you send that across. And then she's sending across G to the B mod P. And then the idea is that each of them then can calculate G to the B mod P to the A mod P equals G to the A B mod P. So they end up with the same number. And then they've got a shared secret. Fantastic. ECC, you can do the same thing. And so we've got the curve, we've got A, and we've got G, the generator, the base point. And she's sending her public key across. And again, it just works out A times, so public key times private key, public key times private key equals essentially generator times private key times private key. So they can come up with the same number. Man in the middle attacks. Okay, so you've got this nasty person in the middle, and so coolstock sends some maths towards Alice. Man in the middle changes A, turns it into M, and then she sends her stuff back, and again they modify it. So now they can see all the they'll agree a secret with Alice, and they'll agree a secret with coolstock, and they're able to decrypt all the communication. So the way to fix this problem is to sign the messages. So if Coolstock signs this message, the man in the middle doesn't have Coolstock's private key, so there's no way that they could break that. Okay. So there's a spec, an IETF document, which specifies a whole lot of parameters that you could use for Diffie-Hellman. And the issue you've got there is one is that the keys and the parameter size is really small. The other thing is if you have everyone use the same parameters, that it makes it really easy for large nation-state actors to have essentially a rainbow table and be able to say, all right, well, if this is your public key, then this will be your private key. So, so maybe you want to generate your own parameters. And in fact, there was a website set up called weekdh.org, which essentially says you want to randomly generate your own 2048-bit Diffie-Hellman parameters and not just use the ones from the spec, because otherwise, you might be in a bit of trouble. ECC though is all good because you're using P256, so it's so big that an attacker couldn't attack it. Asymmetric encryption. So the idea is that anyone can encrypt stuff heading towards you, and you can decrypt it. So whether it be Scott or Brett, they can both use my public key to encrypt, and then I can decrypt, but no one else can decrypt. And so the message goes in here, public key, you encrypt it, you end up with your ciphertext, private key, and we get the plaintext back. So very similar maths again. So there's also, so one of the things with RSA is though it's much slower, much slower. So asymmetric crypto is generally much slower than symmetric. So you've got to use something called enveloping. And so the idea of enveloping is that you randomly generate an AES key, and an AES key 128 bits, so 16 bytes. And so you just encrypt using RSA your, or rather down here, you just encrypt the AES key using RSA. So you only got a small amount of information that's being encrypted. And then you use your AES key to do the bulk encryption. And the reason why you do that is AES is going to be much faster and able to handle the large data size. Like 2048-bit RSA can encrypt an absolute maximum of 2048 bits, which is not a lot of data, is it? And then you've got padding, so it's even less. But it can easily encrypt a 128-bit AES key. And then there's your decryption. So in the ECC world, there's something called ECIES, Elliptic Curve Integrated Encryption Scheme. And so the idea of ECIES is to allow you to do encryption using ECC. This algorithm is one of those great ones for showing you how not agreeing on a standard or having a standard that gives you too many options means that nothing gets implemented for years. So ECIES was around since, I don't know, the late 90s. It wasn't really implemented for at least 10 years. And that's because there were too many options. So nothing was going to be interoperable with anything else. So, which is a major problem. But anyway, so it has been finally implemented and is used in Ethereum. So internally within the algorithm, what you do is you randomly generate an ephemeral key pair. What's an ephemeral key pair? Adrian, ephemeral key pair? Yeah, cool. You watch those sci-fi movies where you had ephemeral beings and all that sort of stuff. You short-lived beings, you short-lived keys. Yes. So an ephemeral key is just, so it's a short-lived key. Yeah. And so you generate a key and a ECC key pair, and we've got A and B. And then you essentially are doing key agreement. So we worked out you could do key agreement to come up with a symmetric key. And so you do the key agreement, and then you throw the private key away because you don't need it anymore. And then you AES encrypt the data, and then you send the data in the AES key and the public key, the ephemeral public key. And then on the receiving side, you get the information, and then you do the key agreement again with that ephemeral public key. and then you've got the symmetric key, and then you're able to AES decrypt, and you've got your plaintext. Voila. Okay, entropy and random numbers. Okay, so PRNG, pseudo-random number generation, also known as deterministic random bit generation, is when you take a seed value and you generate a deterministic sequence. And so there are some older algorithms such as MD5 PRNG, SHA-1 PRNG, which you should generally avoid. And there are newer ones that come out of SB 800-90, which are known to be good, but then you've got to also be careful. There are other ones, such as say the dual ECD-RBG, which have got no backdoors and are no longer in the standards, but are in the older versions of the standards. So it's always good to, know about what the problems were in those algorithms, and know that there are some good algorithms that have been analysed by many people. So entropy is often the weakest point in many systems. And in fact, if you're an attacker, rather than aiming at the crypto, you might aim at the entropy. Because if you've got weak entropy, then it's, you can just say, all right, I've got the source code spec. We're open sourcing, so you open source our code. So we're saying, hey everyone, here's our code. This is how we're going to, the environment we suggest you execute it in, our suggested deployment environment. And then, if the actual entropy is really small, then an attacker could walk through the code and say, well, these are the likely keys. Here we've got 2 to the 50, say, possible values of key, and then, they're away. So you've got to be pretty careful about entropy. So for instance, if you had a server that you flicked on, and when you flicked it on, it got the current time in milliseconds, then, and you know that the server was only turned on sometime this year, then you would have log to 365 days in the year, 24 hours, 3,600, 1,000, 34.8 bits. So 34.8 bits is not a lot of combinations, and you could use that then to break the system. So this is why you've got to be really careful. And in Netscape, which is now 20 years ago, they had this sort of problem of current time in milliseconds as their seeding value, and it was broken. So when you're thinking about what you're going to use, don't trust any one entropy source. If you just trust one entropy source, then the attacker says, aha, I can see your source code, I know what you're doing, I'll attack that entropy source. So the more entropy sources, the better. Intel random instruction is a good instruction to use. It's a good way of gathering some entropy. It should even work in virtualized environments. You could time unobservable random events. So maybe you service some packets inside your server. When you're servicing those packets, you could get the nanosecond timer for the chip, and then fire that in as a little bit of extra entropy. And even if that's only 1 bit, 1 nanosecond uncertainty or 2 nanoseconds uncertainty, it's still 1 or 2 bits. And if you do that regularly, then that will help to kick the entropy along, which is very important. So never trust one entropy source. Use a known good algorithm implemented in a cryptographic library. If you've got AES-NI instructions, consider using CTR-DRBG because it essentially uses AES internally within the algorithm, so it might be really, really fast. But you want to measure the performance of these algorithms on the hardware or the environment you're going to use them in, because you may find that the 256-bit version will be faster than the 128-bit version. It depends on the algorithm. Yeah, and won't be seen often. Okay, Schnorr Signatures, one major section to go. Okay, so I'm going to walk you through some use cases and then talk about how this works. So Schnorr Signatures are useful and were talked about in the Bitcoin context, but now there's talk about them being used in the Ethereum context within sharding, and so worth you to understand. So you've got a sender, and normally they do a signature, and you've got one signature and one for one transaction. But if that sender had 3 transactions that they wanted to send in, and combine into one, then rather than having to do 3 signatures, wouldn't it be great if there was a way that they could just do 1? So, you know, in Bitcoin, you know, you have multiple accounts and you're essentially putting all the coins into one account, or, you know, having them into a different one output. So that's the general idea. How can you do this? How can you merge signatures? So I'll start off with the mod Q version of this algorithm. So you start off with a large prime Q and a generator G, and so everything's mod Q. So whenever you're seeing anything, just imagine there's a mod Q at the end. And so you generate a private key, and which is, you know, a random number, and then you have your public key as Y is G to the X. And so M is a message to be signed, and so you randomly generate K in the range 1 to Q, and then you calculate R, which is G to the K, and then you let E be the hash of R appended with M, and then you've got this value here, and then your signature is S and E, so the hash of the input values. And then you can verify by doing that little bit of maths there. So you can prove that this all works. I'll let you walk through the slides, because there's a bit of maths there, but it's useful to understand. I mean, and it's not too hard. It's really you end up essentially saying, if the values are all right, then RV will equal R, EV will equal E, which is all good. And then for the EC version, again, very similar maths, but we're in elliptic curve land. And so the reason why this is important is that you can do a multi-signature version. And so everyone generates their private keys in that range, and then you have all these public keys. And then you have multiple messages, and then you can then calculate your R value, and then for each signer you calculate the hash value, and then you combine them all together to have your S values, and then you can calculate an overall signature, and by just bringing that together. And remembering it's all mod Q, so even if the number keeps on getting bigger and bigger and bigger, because it's mod Q, it'll be smaller again. So for each message, though, then you can calculate that, and then you get your RV value, and then if the RV equals R, then the signature is verified, and then there's that proof of correctness. So the thing to note about that is, though, that if we're just doing maths, say, you know, Brett, Scott and I are doing this, and, you know, we were each generating the signatures and then combining them together, is it going to be safe? You know, if I've got 3 accounts that I'm using to combine signatures, I can trust myself. But, you know, those guys, you know, not, you know, if it's millions of dollars, maybe there might be, you know, they might try and do something shifty, who knows? So, so if you're going to, you know, you have a last signer problem with this algorithm. And, you know, is there a way of them manipulating the values to somehow or other gain an advantage? So the thing to do is have a commitment scheme to make sure that they can't, you know, once they've committed to, they commit to a value, and then once they've committed to the value, then they've got to publish. So essentially you publish the hash value of your key, and then you publish the actual key. That's what you should do. And there's even a publication which talks to that. Another thing to think about is that a lot of when you see the prime Q version, or the mod Q version, they use 160-bit primes, and I think they're too small. So, yeah. So, summary of all of this, golly, it's really complicated, isn't it? I mean, for those people who've done it for years, it's not so bad, but for other people, I think it's pretty complicated. And, you know, we've done the introduction to security, and now we've done this, and there will be a video on the YouTube so you can watch it again and go through the slides. But it's a start of a very long cryptographic journey. You know, you shouldn't expect to be able to understand all of this overnight. And are there any questions? And I forgot to put a slide in. Down on the Gold Coast, at Griffith University on the Gold Coast, they're running the second Distributed Ledger Forum symposium, should I say, on July the it's a Thursday, July the 6th, I think. Anyway, I'm sure if you hit up Griffith University's website, or if you get in contact with me, I'll tell you how to get to it. It's only about $150 if you get in early, or $200 if you wait. And it's more of a research style conference, but well worth going to. And in 2 weeks' time, Adrian and there, Rob, who's out the back, and myself are going to talk about POW, POS, and POA, and actually in reverse order. So I'm going to do POW, Adrian's going to do POA, and Rob is going to do POS. That's the theory. So, are there any questions? Yes?
I have a two-part question. I think with most algorithms, you're pretty safe that 99.99% of the attackers will not succeed. But then you already mentioned these large state-owned organizations which always try to sneak in some modifications to make it weak enough so they can crack it. As far as I have followed the discussion, NIST had chosen some parameters for the elliptic curves which are used for HTTPS and stuff. And I have the impression that as long as you don't use the latest new elliptic curves, they can actually intercept any encrypted communication. Maybe it's just rumors, but that's my interpretation.
I've heard that, and I encourage you to watch. Bernstein's a great skeptic of this whole NIST thing, and he's a very big promoter of that and new curves. And for myself, I mean, it's possible. It is possible. And so, I mean, you've got to look at the attack vectors that, say, the NSA have had. So you've got DES, which originally was going to be a 128-bit key, and then they sort of said, no, it's got to be 56 bits so that we can break it. And then I guess they published it. But then they quite quickly then released triple DES, because I guess they realised, actually, if we can break it, so can other people. So that was essentially, you could think of that as being a symmetric, vulnerability, where they can break it and anyone else can break it. The ECDRBG, though, was what I would think of as an asymmetric style attack, where they essentially have the private key, and all the rest of the world's only got the public key. And so you're busily generating your bytes using the public key, and if you can do things in just the right way, and you happen to have the private key, then you can break it. And so that's more of a, rather than early to mid-70s, that's more of a 90s, early 2000s style thing. So these curves came out in the 90s. That's when they first started being standardized. And so for, in that era at least, they seem to be, recognizing that if they have a symmetric attack, then if they know something, or if the key strength is too small for some reason, or if you once you have this mathematical breakthrough, then you'll understand this. If they thought that, then they'd realise that maybe the Chinese, the Russians, and whoever else would be able to do the same thing once they had the same mathematical breakthrough. And if it ends up being widely deployed all over the place, including to NATO forces and all that, then that'd be a big problem, I would have thought. So for that reason, my guess is that it's probably okay, but then equally, I think Bernstein's thought is that, maybe they understand, have got some advanced discrete logarithm understanding just for those curves.
Yeah, the other question would be, there are multiple occasions where state actors try to weaken cryptographic algorithms so that they are hard enough for most of the other ones, but not hard enough for them. So maybe they attack some pseudo-random number generators so that the entropy is smaller than they can get in. And my next question would be, if these hardware implementations of AES are trustworthy, or if you can think of any attack vectors that they talked to Intel and said, hey, if you tweak these 2 bits and we know what you tweaked, then we can break AES, but not nobody.
Well, yeah, I mean, you could imagine, I don't know, so, I mean, for conspiracy theorists, hi all conspiracy theorists on the live stream, or watching the video, but you could, if you're a conspiracy theorist, you could say, if you're the NSA, you've agreed with Intel that there's some magic instruction, and if you use that instruction, then you can find out some information about current AES NI instructions. You know, you could imagine that could be something, but then, and I've got no idea whether anyone outside of Intel gets to verify the silicon, you know, I mean, I just don't know, but I mean, I think the thing is, if you don't trust your silicon provider, then you're in real trouble, I guess.
Yeah, of course, you always want to have a performant application.
Yeah.
That's why you attempted to use the hardware implementation. Of course, always go to a really open source, public software implementation, but that would be much slower.
Probably. Well, and I think a lot of the, like if you use, say, OpenSSL, I dare say OpenSSL would, these days, I mean, you'd have to look, but I would have thought that they'd be trying to delegate down to AES-NI where possible, because it'll be faster. You know, and I guess I guess for us, at least in Australia, I guess if you had a hardware manufacturer, you know, like a silicon manufacturer, you know, just depending on the country, you know, you might not trust some other country was, I don't know, maybe Intel and AMD, I'm not sure exactly where they actually do their silicon manufacturing, but maybe you decide you trust them more. I mean, yeah. Okay, are there any other questions? Oh, yeah.
When you were talking before about the elliptic curve cryptography, you used a phrase, I think it was known good curves.
Oh, yeah.
I'm just wondering how you distinguish a known good curve
Oh.
from a bad one.
Yeah, well, I'm not a mathematician, and I'm also not a pure cryptography, or applied, but not pure. So I know how to, you know, combine algorithms together to use them, but actually designing new ones I'm not so good at. And there is actually a website which is about talking about curves and how to, you know, like what properties you should expect. And so you can, say, generate your own curve parameters to generate your own curve. But then there are a whole heap of tests you've got to try and put the curve through to prove that it's strong. And so there are weaknesses that you can have in a curve such that it makes it easier for people to break and break the mathematics inside it. So yeah, that's why in some ways using these known good curves, these named curves, is a good idea rather than generating your own curve parameters. The other thing as well is generating your own curve parameters for ECC curves takes a long time. So, you know, I think it's minutes or hours.
So really it's just because the known ones have been through a certain amount of testing already and withstood the tests.
Yeah, yeah, that's it.
I think the rule of thumb is, as a normal mortal, you shouldn't invent your own cryptographic algorithms or parameters. So concerning the elliptic curves, I would avoid, just to be sure, the NIST curves and use maybe the newest ones which they created thereafter as a replacement. I don't have the number or what's the name of the curve on the top of my head, but you can find it easily do some research.
Yeah, okay. All right. Well, thank you everyone for coming along today. Thank you for people on the live stream, and have a great day. Bye-bye.